Well, let's start. We start with discussing in more detail the Poincare duality theorem for de Rham homology. I have briefly said about it at the very end of the previous lecture, but let us be more precise here. First of all, the formulation in which we will prove that. Suppose that we have an connected, orientable manifold of finite type. I recall that of finite type means that it admits a finite good cover, and a cover is good if any intersections of charts is either empty or diffeomorphic to Rn. So if M is satisfies this property, then we always have the following bilinear pairing. If we have one cohomology class in usual de Rham cohomology, another cohomology class of the complementary dimension in de Rham cohomology with compact supports, then we can get a real number just by taking the product of the representatives and integrating over M. This integral is well defined since the form always have fine compact support, and an easy check is that well, first of all, if one of the forms is exact and the other is closed, then this one is closed. This immediately implies that this is a well-defined pairing on the level of cohomology classes. So if first of all, let us finish the assertion of the theorem. The assertion is that this is a non-degenerate bilinear pairing, which means that both left and right kernel of this pairing are trivial. And in another words, this means that these two vector spaces are dual to each other. So the dual vector space, this space is identified with the space of linear functions on that space, and vice versa. Once again, why this one is well defined? Since if we take representative of cohomology classes, then both forms are closed. If we change one of them by an exact form, so that we are in the same cohomology class, then the difference is like that. It is closed form product with exact form. But then this is, since phi is closed by Leibniz rule, we have this. So this is exact form and its integral is 0. So the result is independent on the choice of representatives. So the non-trivial part is that this is non-degenerate. The part that we have this bilinear pairing is trivial. Well, before proving it in detail, I would like to say what is true without this assumption. If we drop this assumption that M is of finite type, then then what is true? It is true that for an arbitrary M, for an arbitrary connected oriented M, for an arbitrary M, we have the following. We have that if we take cohomology with compact supports and take the dual space, then this is isomorphic, naturally isomorphic via the same pairing to the cohomology of M. But not vice versa. The opposite is not true. This is the usual thing when you have, say, for infinite dimensional spaces, you never can have that two spaces are dual to each other. If you take a space, you take the space of linear functions and you take the second adjoint, the second dual, then it is never isomorphic to the initial one, and here we have the same phenomenon. So this one is true, the opposite is not true. The dual to this space is not that. This is obtained from the case of finite type by certain limit, but I don't want to say about it. This is purely algebraic thing. So we will work only with manifolds of finite type. For manifolds of finite type, as I said in the previous lecture, this theorem is proved by induction. On the cardinality of finite cover. And as we have discussed on the previous lecture, it is enough to prove the step of induction. It is enough to prove that if we have two open subsets of some manifold and we know the theorem for U, for V, and for U intersection with V, then this implies the assertion of the theorem for the union. This is the only thing we need to prove. If we prove this, then we just proceed by usual induction. And now let us discuss how to prove this implication. So assume that we have, we just need to write down two Meyer-Vittorius sequences. One for usual homology and the second one for, I try to get into the one board. If we start with union, go to the sum of cohomology of two subsets, and then to the intersection, and from here we have k minus first cohomology of the intersection, and here we have the sum of k minus first cohomology of U and of V. So we have this exact sequence. This is Meyer-Vittorius. The only non-trivial, all maps are pullbacks along inclusions, except for this one. This is connecting homomorphism. And we have in the opposite direction, we have, I would like to start with n minus kth cohomology with compact supports of the union. But for cohomology with compact supports, we have maps in the opposite direction. They are pushed forward along inclusions. So we have a sequence like that. And here we have cohomology with compact support of the intersection. And here we have again this connecting homomorphism, and we get into cohomology of dimension n minus k plus 1 of the intersection, again with compact supports. And here we have, or not this direction, n minus k plus 1 of u plus cohomology of dimension n minus k plus 1 of v. Okay. So we have these two Meyer-Vertores sequences, and we know from the induction hypothesis that each pair of spaces here, except for the middle one, is dual to each other. This is just by induction hypothesis, and moreover, the pairing is given by such formula, is given by taking the product and integrating. It is not so convenient to work with pairings. We prefer to work with maps. To work with maps, what we need to do, we need to write, to pass to dual spaces in this sequence. I don't want to write it down again, so I write it down like that. That we take yes, the duals of all this. So here is this space, here is that space, and so on. And of course we have maps in the opposite direction. We have maps from here to here. Pairing gives, we have this pairing. Pairing gives maps, homomorphisms from here to here. And by the induction hypothesis, we know that all except for the middle one are isomorphisms. And now it is just the standard 5 lemma, but I skipped one important thing. To be honest, we need to check something.
Maybe that when we take dual, it remains to be exact?
Actually, no, it's standard fact that if we have, this is over a field, we have finite dimensional vector space, and the exact sequence certainly becomes exact sequence. But
chain maps, commutativity.
Yes, it's, we should check that this diagram is commutative. And it is completely trivial in all these squares. Commutativity is obvious. Indeed, well, if you have a form on U and a form on V, then of course you can let me skip it, but it is completely obvious that we can integrate on one on a smaller manifold or on the larger, and the result is the same if the support of a form is in the smaller manifold. So the only slightly non-trivial thing is the commutativity in this square. Here we have the joint of this operator. So here we have this connecting operator, and we take the joint of it. And here we have that connecting operator. And actually, a priori, it is not so obvious, but we have a nice exact formula for both this and these connecting operators. And both of them were, all these operators are up to sign. We can change sign whatever we want. And both of them were given by plus or minus. I don't want to think about it. We need to multiply our form phi by the function from partition of unity, and then to take the differential. And here we have the same formula, but actually I would like to recall that these two formulae have different meanings. They are written in the same way, but the meaning is different. Look, here in the upper, we have a form on the intersection. We have a form in this setting, in the first. We have a form on the intersection. We multiply it by function rho u, and function rho u has its so we have form on the intersection, and function rho u is form which lives on u. Well, multiplying them, we get form which is again on the intersection, but we can extend it by 0. So here we mean extending by 0, yes? And here the situation is opposite. We have from the very beginning the formula on the whole manifold. And then we multiply it by rho u, and we know that rho u has its support only in u. So our form has support in u. On the other hand, this is the same as to take rho v, because rho u of phi plus rho v of phi is a closed form, is the closed form phi. So if I take here the differential, then I get this 0. So similarly, its support is in v. So in fact, the support of this form is always in the intersection, and we consider this form as the form of intersection. Okay, but once we write down this, it is completely obvious that this is this square is exact. It is just integration by parts. If we take this is integration by parts in this pairing. We can change differential from one form to another by using integration by parts. So okay, that's the finish of the proof. Well, now, yes, of course, one of the most interesting cases is when the manifold itself is compact. Then, of course, there is no difference between usual cohomology and cohomology with compact support, and we can yes, and we have this duality inside usual cohomology. So let us discuss this in somewhat more detail. If M is compact and still connected and oriented, then it is automatically of finite type, and we have this duality defined in the same way between between usual cohomology in both spaces. In particular, we again see in the other what we know. We know that H0 of M is of course compact, connected, and oriented. Isomorphic to R, H0 is just constant functions, and so the dual is also R. And we have already discussed that yes, this isomorphism is obtained just by taking the integral of the form over M. And so, for instance, a representative here is the volume form. What is another possibility to look on this Poincare duality? Cohomology of M is a ring. Yes, it's a ring, and so we have multiplication in it, and in particular we of course have such homomorphism. This is just multiplication, and we know that this is R, and this is the same homomorphism. Of course, we multiply and then integrate, and this is exactly the same. This is not something new, but this is just I would like to say that this is the same. Okay, and actually this is one way to understand Poincare duality. Yeah.
How we understand that Hn of M is R?
Again, by Poincare duality. We know that this one is R, so the dual is also R, and the isomorphism is by pairing with function which is constant 1. So that's just this says that cohomology of M is actually, this is an important thing even purely algebraically. It's an important thing algebraically that when we have a graded ring such that it has finitely many terms, finitely many gradients, the highest of them is the field, and the lowest, and this one, this is non-degenerate in any other dimension. This is called Poincare duality algebra, and this is a very important thing that we get such good algebra. Okay, but I would like to discuss that there is another point of view from which Poincare duality is very natural. This is so-called Hodge theory. Just I would like to briefly recall it. It will be useful to us sometimes, but so let us discuss Hodge theory. I will discuss only real part of Hodge theory. We are not going to go into complex things, and I will say here only of the case of compact oriented connected manifold. We again can extend it to non-oriented to non-compact case, but no, I don't want to try to do this. Okay, so first of all, what is important? An important thing, and it will be important to us not only in understanding Poincare duality, but also further, that we have, well, suppose that we choose here a Riemannian metric. So this is a Riemannian manifold. We will choose and fix a smooth Riemannian metric on our manifold. And then look at every point P, we have tangent space, and we have its dual cotangent space, and so we have tangent space at P, we have cotangent space P, and we have its exterior powers of cotangent space. And once we have a Riemannian metric, these tangents, all these are just, this is just linear algebra. These are just finite dimensional vector spaces over R. I would like to start only from one point, at point P. We have here Euclidean scalar product. Let us denote it by such an angle brackets. Riemannian metric is nothing but a Euclidean scalar product here. Hence, we automatically get Euclidean scalar products here and here. This is a good exercise on in linear algebra that if we have here in some space, if you have an orthonormal basis, then if you get elements like that, then we can take this for orthonormal basis in the exterior power, and well, the claim, the assertion is that this is well defined. The obtained scalar product on kth exterior power is independent of the choice of orthonormal basis here. So, well, this is just pure linear algebra that we have good scalar product at every point. But now, a non-trivial thing. A non-trivial thing that now we can introduce a scalar product on an infinitely dimensional space, of k-dimensional forms, of k-dimensional smooth forms on M. Consider this is, I would like to stress that this is a product just in one point, and to stress this I use index P here. P is a point. And how to introduce a scalar product here? So I would like to introduce a non-degenerate bilinear form from here, the symmetric bilinear form to R. If we have two forms, two K forms, both of them are K forms with the same K, then we can proceed as follows. We can take their products at every point P, and we can integrate this by the volume, multiply by volume form. Since it's a Riemannian manifold, we have a well-defined volume form here. Let it be omega, and integrating over the whole M. We see that this is indeed a scalar product. It's of course bilinear, symmetric, and also it is positive definite. Sorry. Yes, of course it's a positive definite. If we take here the same form, phi, then there exists at least one point where this phi is non-zero, and at this point, and in its neighborhood, we get positive function here. So we integrate some non-negative function over M, and this function is positive in at least one point in its neighborhood. So hence, we get a strictly positive integral. Well, and it is important to distinguish between this local scalar products and global one. It is not. It is very important that we use different brackets to distinguish between them, because they are of completely different nature. This local is just depends only in one form, only at one point, but global depends on the picture of the whole manifold. Well, and what can we say? Yes, and there is an important Hodge star operator. Which this is a purely algebraic operator. It actually acts in every. So this is not the subject of differential geometry or something like that. This is a subject of an object of linear algebra. If you have got a Euclidean finite dimensional Euclidean space, finite dimensional Euclidean space with fixed orientation, and what does it mean, fixed orientation? Fixed orientation means that we have the volume form, which is just, if it's n-dimensional, then the volume form, again, we have it's just in one point, it's just an element of nth exterior power, which is just R, yes? And we choose this volume form, and once we have such data, we have a natural star operator from kth exterior power to n minus kth exterior power. And the idea is that, of course, well, the idea is that just to have that, we would like to have this property. Not to miss some signs, no signs here. Here it's okay. We would like to have this property, well, such Hodge star exists and is unique. Why? Because the pairing between kth and n minus kth to R is non-degenerate. This scalar product gives non-degenerate. No, not scalar product. This exterior product gives non-degenerate pairing. So this is just an. The right-hand side is a linear function in phi. Hence, let us fix psi, and then the right-hand side is a linear function in phi. So there is a unique element here such that we get this. It is not hard to write it down explicitly. Namely, if we have an positively oriented orthonormal basis, then we always have that if we take the first k of them, then we get just the product of the last n minus k. And this determines the star completely, since any element can be written as linear combinations of such elements. So what is important and what is easily seen from here, that if we apply star twice, then we get plus or minus 1, but this depends on the degree of the initial form. This is exactly minus 1 to the power k times n minus k. The matter is that if we take the first k, we get the last n minus k, but then to apply it to this, we would like to change these k and n minus k to make these the first, and that's the last, and we get this sign. Okay, so this is an element of pure algebra, but now we can apply this at every point. By applying this at every point, we get star from k forms on M to n minus k form on M. And what is important, it is important that this is purely local operator, very local operator, in a sense that, well, differential of a form is also local operator. The differential of a form at a point depends only on a form in a neighborhood of this point. But here we do not need a form in the neighborhood. Here star of phi depends only, star of phi at point P depends only on form phi at point P. Only on the point, so this is not differential, this is algebraic. Pointwise operator, yes. And it is defined by this property uniquely. Well, so okay, we have this nice operator, but also we have this global. So this thing is local. This star is only in every point, and this one is global by its nature. Once we have this is much more non-trivial. This is non-trivial thing. Once we have this non-trivial global scalar product, if we study some operators in a space with scalar product, it is very natural to consider adjoint operators. We have one important operator in the space of forms. We have exterior differentials. So it is very natural to study the adjoint of this operator with respect to this non-trivial scalar product. It is denoted either by d star or by delta. It's just two standard notation for it. It goes from k forms to k minus 1 forms, and it is the adjoint of D with respect to that scalar product. The adjoint of D with respect to that scalar product. A good question is it is not so. So what is the definition? The definition is that we would like to have that d star phi psi equals to phi it's the same. I just prefer for the sequel to write down like that. It's no difference, of course. A good question is why such an operator exists. We know from linear algebra that adjoint operators should exist. But here we have not completely a linear algebra. The matter is that, okay, adjoint operators exist, but they exist in adjoint spaces, in dual spaces. If you have operator from V to W, then adjoint operator goes from W to V. The matter is that, of course, it is not true that this vector space is dual to that vector, to itself. It is infinite dimensional, and of course, its dual have basis of just greater cardinality, so it is not the whole. In fact, we are here not in the world of linear algebra, but of the world of functional analysis. We would like to work with infinite dimensional vector spaces. In fact, we want to work with some topology in that vector spaces, but up to now I said nothing about which topology we consider here, and I don't want to say which topology we are consider. But why such an operator exists? So it is not obvious that it exists. It is not by definition. Why? An obvious thing is that it is unique. We cannot have two operators with this property. If we have two such operators, then the difference between them of psi will have trivial scalar products with all forms, and hence is zero. Uniqueness is obvious, but existence is not obvious. And why it exists? Because we can write it down explicitly. Of course, there are other variants to prove that it exists, but let us make a small but important computation. So let us start with this left-hand side. And well, I would like okay, let here phi be k-1 form and psi be k form. Just I would like to denote by some letter the degree of a form. I prefer to use k for the degree of psi. Well, by definition of the scalar product, it's differential over M of such integral of such local scalar products. It is just by definition. Now, what can we do? Using the definition of the star operator, we can rewrite this expression at every point, and we get here d phi multiplied by star of psi. This is just by definition. Now, we can use the integration by parts. We have that d of phi times this is d phi. I prefer to use brackets here. D phi times star of psi plus -1 to the power k-1. I would like to be careful about signs here. K-1, since phi is the k-1 form of phi d, and here is d star psi. So we first apply star and then d. We have a formula like that. The integral of this one is of course 0, since we have a compact manifold without boundary. So the integral of this one is opposite to the integral of that one, and we can write it down. Here we get -1 to the power k, since here k-1 and 1 minus, and here we have integral over m of phi multiplied by d star psi. Okay, and now we again use the definition of the star operator. Star operator is isomorphism at every point. So again, this is local equality. This is not only equality or equation between integrals, but it is equality at every point. And here we again have such local equality that here we would like to write down -1 to the power k of scalar product at local scalar product of phi with, here I have star inverse d star, and multiplied by volume form. This is again the definition. First of all, star inverse exists and is unique. Star is an isomorphism, so it's okay. And this is again the definition of star operator. And again, what does it mean? That first of all, I would like to use star instead of star inverse. I know that star squared, if we apply it, oh sorry, here is psi. If we apply it, look, this d star psi, what is the dimension, the degree of this form? K form, n minus k form, n minus k plus 1 form, yes? So if we apply star squared to such form, then the sign is -1 to the power k plus k minus 1 times n minus k plus 1. Sign is like that. It is not very important which sign is it is. So if I change this star to the minus star reverse to usual star, then I get this sign. So which sign is in the result? Look, here I have k minus 1 times n, or k plus 1. It doesn't matter, since I'm interested only modulo 2. Yes, k squared and k disappear, and we have here also k plus 1. Yes. Sorry. K squared. This is no, just one. Well, yes, just one. And here we have integral. So then we can delete this -1, but this is nothing but phi multiplied by star d star, again by definition of this global scalar product. So this small computation shows us that we can write down the operator d star explicitly. Oh yes, here is psi. So the operator d star or delta is nothing but the operator star d star, but with some sign which depends on the degree of the form, and sign is k plus 1 multiplied by n plus 1. And this is differential operator. This star is not differential operator. This is just algebraic operator. And then we take the exterior differential and again apply this star. So this one is differential operator. It is called codifferential. D is differential and this one is codifferential, but it is just some differential operator. It is sometimes they say that this is formally adjoint of operator. A true adjoint exists when we have say Hilbert space, or not just what is the difficulty here? The difficulty here is that by no means this is a Hilbert space. This is a vector space with non-degenerate scalar product, but it is not complete. We have there is no good topology for which it is complete. The matter is that getting a limit of smooth functions or smooth forms, we always can obtain as a limit in any topology we invent. A limit can be non-smooth. We cannot invent a topology so that it becomes complete and Hilbert space. So here we have some analytical difficulties, but not in the, there is no difficulty in definition. We can write it down explicitly, and so we do not need any hard theorems to say that this operator exists, since just an easy computation shows us that we can write it down explicitly. Okay, and now, what is Hodge theorem, which is not so easy, which is in the proof of the Hodge theorem we cannot avoid analytical difficulties, and I will not prove it in detail, but and at all I will not prove it. What is the idea? The idea is as follows. Suppose that we would like to study, let us keep in mind this formula, but I delete this.
May I ask a question here?
Yeah, sure.
For the last step, how do you turn the star inverse into star?
I know that star squared of some form, I have said it, is plus minus this form. And this plus minus is minus 1 to the power of k and minus k, where k is the degree of the form. So star inverse is just star up to this sign. And this is exactly what I did. Okay, now I remove this computation. And what I want to say, that assume that we are interested in some particular cohomology class. I would like to study a cohomology class of manifold M, the RAM cohomology class. How can I look on this? I can look on this in the following way. Let us consider the vector space of all closed forms. Then what is a cohomology class? A cohomology class, here we have 0. A cohomology class is a coset of exact forms in closed forms. The cohomology class is not a closed form, it is a closed form up to exact forms. So we have a coset of exact forms in a affine space, a affine plane in the set of all closed forms. And a natural thing is the following, that once and now in this space of closed forms, and actually this closed forms this is a subspace of all k forms on M. Well, now we have scalar product here. So this is not only a vector space, but this is a Euclidean vector space. And once we have a Euclidean vector space, then a very standard thing is to say, okay, let us choose here the shortest representative. Let us just consider the perpendicular to this affine plane. And maybe this representative is the best one. So we can choose inside this phi, inside this x, the form phi of minimal norm with respect to this scalar product. So we would like to minimize this norm, where this norm is just the square root of phi phi. Yes? And what can we see? If we find such phi, let's assume that we have found such phi, then what we see? It should be orthogonal to every exact form. Well, so we would like, if we have found such phi, then what we see? We see that it is orthogonal to every exact form, But this immediately means that we can rewrite it as d star phi psi. And we see that this is 0 for all psi. Well, what does it mean? For all psi, this means that d star phi must be 0 if it has 0 scalar product with all forms. Hence, d star phi is 0. And look, actually, this is not only implication, the opposite implication is also true. Well, if it is 0, so this phi is uniquely determined by this condition. So this is the form such that d star of it, codifferential of it, is 0. So, but since it's closed, then we have that d phi is 0 and d star of phi is 0. And such forms are called, by definition, are called harmonic forms. And what we see that here we have a form with this property, but actually this is a hard theorem. What is a hard theorem? The matter is that if we were in finite dimensional vector space, then of course we can take the perpendicular to a plane, and that's okay. If we were in a Hilbert space and this one were a closed subspace, we again can put a perpendicular and take the phi with the smallest the phi with the smallest norm. If we are but we are in a infinite dimensional vector space, which is not a Hilbert space, which is not complete. So there is no it is not obvious at all that there exists such phi, and it is namely a priori it could happen that the situation is as follows, that we do not have a minimal a phi with minimal norm in the original space. It could lie only in some completion of the original space. So it may happen that the minimum is achieved on a non-smooth function form, but it never happens. The theorem, the Hodge theorem, is that in every cohomology class there exists a harmonic form. In every cohomology class there exists a C infinity smooth harmonic form. It is non-trivial, and it is analytically non-trivial theorem. To prove this theorem, we need to consider different completions of this space of smooth functions. Namely, these are so-called Sobolev spaces. We consider completions with respect to different norms and so on, and we need to study them all together. And this is indeed a non-trivial analytic fact, and as far as I know, there are no proofs which avoid these analytical difficulties. So this is not, there are no proofs that are more or less algebraic, geometric, something about differential geometry without going to hard functional analysis. So we will not go to these difficulties. Just this is a good fact, and we know that we always have such form. If we have these forms, it is once we know this theorem, it is good to look on these forms in the following way, that once we have this theorem, then it is convenient to introduce so-called Hodge-Laplace operator. Yes, just one. I'm sorry. I don't want to say how to prove this theorem, but I would like to stress one important thing, why it is non-trivial. The matter is that why we need different completions of smooth forms, why it is not so easy. The matter is that standard, functional analysis, the simplest part of functional analysis concerns bounded operators. If you have bounded operators, say in Hilbert or in Banach space, then you have nice theory. This is one part. But an important thing is that the differential is by no means bounded. If you have, functions like that, you can have functions with very small norm, but which oscillates with high speed, and the derivative will be large. So it is not only on exterior differentials. No differential operator is bounded a priori in any good norm. So you need to use different norms. It becomes bounded only if we use different norms in the domain and in the image spaces. So this is just where the difficulty lives, but I don't want to say more about how to overcome it. But okay, Hodge-Laplace operator is by definition the operator like that. It is formally self-adjoint. Formally what does it mean? Of course, yes, first of all, this is an operator from K forms to K forms. It is nice to have operators from some space to itself. So it's from K forms to K forms, since D D make the degree once increases by 1 and D star decreases by 1. So, and of course we have such equality. It's immediate from the fact that D and D star are adjoint to each other, and but formally self-adjoint means again that we are not in a Hilbert space, and we have not all nice things with true self-adjoint operators in Hilbert space. And a nice, an easy and nice idea is that these two equations can be rewritten as one equation. They are just equivalent. And this is an easy computation like that. It is d star phi plus d star d phi, and we have here d star phi plus d phi. And so, well, if this from right to left it is trivial, but just by definition. And from left to right, if this is 0 and this is if this is 0, if delta phi is 0, then we get that both of them are 0 since they are non-negative, and so harmonic forms are just forms in the kernel of this Hodge-Laplace operators. This is a convenient way to think about them. And also one thing which I want to say about this Hodge theorem and about this situation, that actually this is the same phenomenon as the phenomenon of holomorphic functions. When you have complex analysis, you know this strange thing that once you have a function that have one derivative, which complex derivative, then it becomes C infinity smooth. Once only one derivative, we require only one derivative, but automatically get that it has derivatives of all orders. Here, in some sense, it's the same. The matter is that certain differential equations, in partial differential equations, in complex case Cauchy-Riemann equation, here this Hodge-Laplace equation, immediately require that their solutions are C infinity smooth. So this is the same. This equation requires that its solution is C infinity smooth. This is so-called theory of elliptic operators, but okay, we will not go further in this way. We only use this theorem as a black box. So, okay, and what I started from. Oh, sorry.
10 minutes.
Yeah. I have started from Poincare duality, and I would like to say something about how this Hodge theory is related to Poincare duality. It is related by a very nice way. Well, what we see that, look, in every cohomology class there is a unique harmonic form. What does it mean? And vice versa, any harmonic form is closed, so it represents some cohomology class. So there are as many cohomology classes as harmonic forms. So we have just an isomorphism. For each compact-oriented connected manifold, we have an isomorphism between de Rham cohomology and harmonic forms. Let it be H calligraphic. This is harmonic K forms. And now on the level of harmonic, on the level of harmonic K forms, we can easily see that K forms are isomorphic to harmonic n minus K forms. How to see this?
By Poincare duality.
No. We just may see it immediately. This is just Hodge star. So this is just star operator. Indeed, we know that D star is, I don't want to worry about signs, but it's star D star. So what we see, that if an original form was harmonic, so we have D phi equals 0 and D star phi equals 0, then D phi equals 0 rewrites as this is equal, turns into the for star of phi. This equation yields that it is exactness yields co-exactness, and co-exactness yields exactness. And again, we again get a harmonic form. So here we have not pairing, but we have a complete isomorphism. It is not surprising if you have just a vector space and it's dual vector space, then usually they are not isomorphic, canonically isomorphic to each other. But once you have a scalar product, they become canonically isomorphic to each other. So it is not surprising that here we have an isomorphism rather than a pairing. But what is surprising is that this isomorphism can be written just very explicitly. It may, the first, we may think that maybe this is the very good point of view, and further we can just work with only with harmonic forms and not think about any non-uniqueness of a representative and just work with harmonic forms. Poincare duality is very nice and so on. What is not good in this approach? Not good in this approach is that we lose multiplication. There is no good description of multiplication on this language. The matter is that the product of harmonic forms is not. When we take the product, we get some representative of the corresponding cohomology classes, but it is not harmonic. Generally, the product of two harmonic forms is not harmonic. So we still cannot go to this viewpoint completely, but we still can use it. It is useful. Well, and now I would like at least begin. I hope that this will take part of the lecture, and the second part will be denoted to Thom isomorphism. I would like just to begin and say some easiest form of Thom isomorphism, and on the next lecture we'll proceed this. So let us consider one important consequence of Poincare duality. An important consequence is like that. Assume that we have an oriented manifold of some dimension m, oriented smooth manifold, not necessarily compact at the moment. And assume that we have a vector bundle over it of dimension n and again oriented. So I assume that all things are oriented. M is oriented and the vector bundle is also oriented. Once we have a vector bundle, its total space is certainly also a smooth manifold. It's a smooth manifold of dimension m plus n. And what can we do? Let us start with kth homology with compact support of m. What can we say using, yes, suppose that it is oriented and it is of finite type. So that I can use Poincare duality in full generality. Then of course E is also finite type. We just can take pre-images of good cover and it is a good cover of E, so it's okay with this. First of all, by Poincare duality for M, we have that this thing is the dual of compactly supported cohomology R is the vector space dual to cohomology of complementary dimension m minus k. Now we know that usual de Rham cohomology is homotopy invariant. Of course, this projection is homotopy equivalence. Yes? Vector bundle, of course. So we can replace here M with E with the total vector space. But now E is again an oriented manifold, but now of dimension m plus n. So we can use again, this is Poincare duality for m. This is homotopy invariance. And this is Poincare duality for E. What we get? We get here cohomology with compact support of dimension. I should take m plus n minus this dimension. So I get here k plus n. Of E. This is a very nice, as a result, if we skip the intermediate stages, we get an isomorphism between compactly supported cohomology of the base and compactly supported cohomology of degree of nth large. This dimension is by n greater than this one of E. This is called Thom isomorphism by French mathematician René Thom. Thom isomorphism. And an important ingredient of this isomorphism is that, for instance, in particular, we have this isomorphism for k equals 0. For k equals 0, we get that this compactly supported cohomology. Yes, and in particular, it is in particularly interesting when now suppose that M itself is compact. Of course, E is not compact at all. If M is compact, then we can skip this C. If M is compact, we get that usual de Rham cohomology of M is naturally isomorphic to compactly supported de Rham cohomology of total space of the vector bundle. And in particular, we have this for zeroth cohomology here and nth compactly supported cohomology here. Here we have the standard generator, which corresponds to to constant function, which is constant 1. And the corresponding generator here is called Thom class, and it will play important role in the future. So it is an important look for this E. We can say that compactly supported cohomology is actually 0 below this dimension. Below dimension n, we have negative k here, so cohomology is of course 0. And in dimension n, we have that this is R, and we have this important representative Thom class, and it will play important role in the future. I'm sorry for I'm late today, but so let us now finish.
Можно вопрос?
Да.
Почему в доказательстве вы Poincare использовали ориентированность? В одной из проверок коммутативности, вот там где?
Да. Что когда мы интеграл берем, то там нигде минус не вылезает, что там действительно все коммутативно по-настоящему, не с точки сюда знака.
Ну, в принципе, если у нас нет ориентированности, у нас же нет фундаментального класса, надо интегрировать.
Ну, да, мы вообще-то не знаем, как интегрировать. То есть, на самом деле, у нас спаривания нету. Как бы. Сначала надо построить спаривание, а потом уже доказывать, что оно не выраженное. А если нет ориентированности, то у нас спаривания нет. Ладно, давайте сейчас. Не выключается. Well, I have no new list of tasks for today because we have discussed most of the problems from the last one. If you need this list from the previous, please just go here and take it. I have some more of them. One moment. Yeah. I'm sorry about for those who are listening here from online. I am sorry for forgetting to send this list by email to those who asked me. I will do it just today or maybe tomorrow, but at the moment I forget to do this. Okay, let us start with finishing the boring story with CPN. I'm sorry for the third time we still are trying to do this, but it's actually an important example, and I would like to write down the answer. Actually, we almost did this last time. If we consider C n plus 1 without 0, then we can write down the following two forms. I just would like to write it down in coordinates. Last time we discussed that this form is obtained just by the geometric idea is that we would like to have two form, which is un plus 1 invariant, yes, which is invariant under scalar multiplication, invariant under scalar matrices, and which also vanishes. We would like to see, okay, at every point here, if we have a point, this point is let it be P, yes? Then we have we are just in vector space, so this V is itself a vector, and we have vectors P and IP. This vector and so these are just vectors which generate one-dimensional complex vector space spanned by this P. And we would like that P and IP in the kernel of these two forms. In the kernel of this form. Okay, we would like to have two form here. Two form on this Cn plus 1 without 0. Why these two properties are important? These two properties allow us to say that this form is well defined on CPN. And last time we discussed that the natural idea is to take, if we have here an arbitrary Xi and eta, and arbitrary two vectors, then we can take their projections on so our form of Xi eta. We can take the projection of Xi on the orthogonal complement of this two-dimensional space spanned by P and IP. The projection on the same space, well, let it be U, the space spanned by P and IP, and U, the projection on the same space of eta, then we can take the Hermitian vector product, and I would like to have a skew-symmetric function, so we should take imaginary part of it, and also to get that it is invariant under scalar matrices, we need to, it's a very good idea to denote it by p, let it be z. I'm sorry, it's very, very bad idea. To denote it, to divide it by z squared. Then it's okay. Yes? It satisfies all. It is by the very definition, it is invariant with respect to unitary operators, it is invariant with respect to scalar matrices, and z and iz are in the kernel of this phi because they go to 0 under projection. If we compute this, then in coordinates this can be written as and we almost done this last time. First of all, the sum over alpha the sum over alpha and beta of this is almost what we have written last time. This is a standard way to write the formula which we obtained in last time. What we see here that this is up to some maybe here. Sorry, and this guy is imaginary, so we would like to multiply it by I. Last time I wrote divide by I by it's just opposite sign. This sign is better. Well. So this is the imaginary part of the usual Hermitian Fubini-Stadi metric. This is what we have discussed. It is a good and easy exercise that this is the same, and we almost completed this exercise last time, and let us not return to it. This is in homogeneous coordinates, and it is a well-defined form on CPN. Why? Because it satisfies these two conditions. It is if we multiply by scalar, then we see here, and also this condition, it is easy to see it in coordinates as well. Okay, so what happens if we pass to, on CPN, it is convenient to work in chats sometimes, not always, but sometimes. What we see if we pass to some chat, what does it mean that we pass to some chat? This means that what is the relationship between homogeneous coordinates and non-homogeneous coordinates? We can just put one of homogeneous coordinates to be 1. Yes, they are defined up to multiplication by constant. If we normalize Z0 to be 1, and then it is usual to denote these non-homogeneous coordinates, but by small Z0, Z1, Zn. So what we need? We need just to go here and to take Z0 1 to substitute here 1 instead of Z0, and to replace all other Zi's but by that small, but then of course dz0 just disappears. Once that 0 is constant, it disappears, and this, so in non-homogeneous coordinates, this function, this sum takes also a very nice. Now that summation was from 0 to n. Here summation is from 1 to n, so I use another indices, just j. Here we have this is j times this is j bar over, and here we get 1 plus modulus z squared, because modulus z small is we have also this one, and here we have minus sum of j and k, zj bar zk, dzj dzk bar over 1 plus. So this is how the function is written in, the form is written in non-homogeneous coordinates. Okay, of course we can live without coordinates, but the next question which I want to ask, it is not so convenient to answer it without coordinates. And the next question, well, we have a two form. First of all, the question is why this two form is closed. Well, so claim is that this two form is closed. There are several ways to do this. Actually, this thing can be done without coordinates, can be done in invariant terms. Just we can prove that there are no three forms which satisfy this properties. It must be, the matter is if the form is invariant, then its differential is also invariant, but there are no invariant forms with this property, but still it should be proved. Well, and in this form it is just an easy computation. I insist that I suggest that you try to do this. It is not hard, but it is a useful computation that, but of course we will not spend time for this, that this form is exact. Oh, sorry, closed. This is just a direct computation. You compute phi and you get 0. And hence, this is exactly what we wanted. From the very beginning, we would like to obtain a generator of two-dimensional cohomology of CPN. And now we are very close to this. We have found a closed to form. So this particular form phi is closed. Well, as I say, it's very easy. It's just differentiation. But okay, it is useful not only to differentiate but also to integrate forms. And so the second question is, of course, the second question is why this form is not exact.
No, we have explained it before. We can pull back this form on some complex line.
Yes. So we would like to understand that this is non-zero. And actually, it is useful not only to understand that it is non-zero, but to understand what it is.
It is P.
Yes. Can you explain why?
No, it is by Dirichlet computations. We go to usual x, y coordinates, and we.
Can you just show the
for n equal 1, the form.
Huh? разумно интегрировать по какому-нибудь двумерному многообразию, а больше мы никакого не знаем. Ну, самое простое, вы знаете.
Minus. What is it?
We have only one coordinate, so here we have only one summoned. It's just model z squared.
Yeah. It would be when we go to the same
Denominator.
denominator, we will get something like no, yeah, I'm ignore this part.
Okay.
And invariable x, xy we would have which
Yes, there are two standard normalization whether we can write here over 2 or not. So we use opposite one on the left and on the right. So
no, I choose fraction.
yeah. I just add here over 2. Well, it is not important until we compute the integral. It's just we took any form.
Hence, we would have something like minus.
No, without minus.
Yeah, but,
Minus I
yeah,
times I. Yeah.
So it's toughest to just to compute this integral.
Yeah.
And so when we go to polar coordinate, we would have something like would be and this integral it is easy to compute.
Yeah.
This would be can I go on the left side?
Yeah, sure.
Would be and this what is it? Something like this. And this would be sorry, good.
Yes.
This
Yeah.
yeah. So we get by
Yeah, thank you very much. Well, This is a nice computation, but what have we done? The matter is, what do we see when in our picture? Actually, when we integrate it over CP1, we can, from the very beginning, we can take not CPN, but CP1. Yes? This form restricted to CP1 is the same as the same form for CP1. What is this? What is?
Sorry, remember we can identify this with two-dimensional
Yes,
sphere,
it's.
and the restriction on form of a sphere would be the volume form.
Yes.
But we know what is the
Yeah,
area
yeah,
of
yeah. Its invariance with respect to unitary group immediately says that this is form proportional to the volume form, to the area form, to the usual area form on S2, and actually this computation is nothing but the computation that the area of two sphere is 4 pi. But just the only thing we need to understand is what is the normalization. If we look through it in detail, then we understand just that we compute the area of a sphere of radius 1/2. So we get pi, and it's not surprising. Actually, if we look on this, yes, then this is 1/4 of the standard area form on the sphere in stereographic coordinates. If you take sphere and consider stereographic projection on plane and write standard round metric on sphere in stereographic coordinates, then you get, and write area form, then you get just this with 4 here, and with 4 you get 4 pi, and without 4 you get pi. So anyway, this is a completely nice computation, and it is so the answer is as follows. The best possible way is to put here 2 pi. Then the integral would become 1. So it was pi. Now if we put here 2 pi, then the integral becomes 1. So this new phi just integrates to 1. It is actually nice to have forms which integrates by integral numbers, such that the integrals are integral. Such forms play important role in algebraic topology, and this is the first example of characteristic class, which the relation with characteristic classes will appear later, but actually this is a standard phenomenon that some forms used to have integrals. I'm sorry for this problem with words, but when we integrate by manifolds, we get. Okay, so can we now compute the total cohomology ring of CPN? We would like to understand what is the cohomology ring, de Rham cohomology ring of CPN.
In general, I think that we can show that exterior power of our form is a volume form.
Yeah, that's the first
Why
question.
we have a subring of form. No, we know that if we take power of this form, it never would be 0. No, until we get to exterior.
Yes,
So
and
we have some good subring,
mhm.
and what's the
So
complicated case, maybe how to show that we don't have anything else.
yeah, so we obtain 2 tasks. Let us. They are not completely agree with the tasks in the list, and don't worry about it. So problem 1. Problem 1 is to compute the integral of the power. We have first of all, we would like to see that it is non-zero. Then we know that once we prove this, once we see that this is non-zero, we understand that in every even dimension, okay, how the cohomology look like. We have here dimension 0, 1, 2, and we would see that up to 2n, yes? This is a real dimension. We would see that here we have R. No, here we of course have R. Here we have at least R generated by the cohomology class of this phi. In dimension 4 we have at least R generated by the cohomology class of phi squared, and so on up to phi to the power n. Look, if you compute this and this is non-zero, then we have the same computations for intermediate k. This is the same claim. So we get that all of them are non-zero. And we get that we have R's all here. And problem 2 is to prove that, so what we see, if once we compute this and understand that it is non-zero, we arrive at understanding that inside our cohomology ring there is a subring isomorphic to how it is called, truncated polynomial ring. We have polynomial ring, so cohomology of CPN definitely contain a subring which is the polynomial ring quotient by the ideal generated by un plus 1. And the actually problem 2 is to understand properly that actually it is isomorphic. We have nothing but except for this ring. So we have this phi and its powers and nothing else. So I suggest that we think about these two problems. There are two ways for this integral. We can either compute or think. Actually, we can prove it without any computation, or we can compute. Both are possible.
We can say that in point 1000 we know that our form will be just, она будет, короче, стандартной и невырожденной. Значит, во всех точках будет невырожденная, потому что она с помощью диффеоморфизма туда переносится. А если она на форму не вырождена, то ее старшая степень тоже не вырождена.
Yes, it's enough to understand that it is non-zero, but it is useful to understand what's the value. Why it is useful? Because, in fact, I say that there are a lot of integrality results in topology. It is useful that integrals of some forms are integral. I'm sorry. This is why people used to say periods of forms along cycles, not to say integrals are integral. Periods of form along cycle, the period is the same as integral. If periods are integral, it is important thing. We can use this integrality result in some understanding of manifolds. But to understand which form is integral, we need to understand, here it becomes integral if we add 2 pi. If we look without pi, then the integral is not. And the question is what you should write down before phi to the power n to understand that. Well, and problem 2 is completely independent of this. Assume that we understand that it is non-zero. Why we have nothing but this? Why there are no other ingredients of cohomology? Well, and also also there are some problems in the list. I'm sorry, I just in the problem 2, RPN is very non-interesting case. This is my mistake. An interesting case is as follows. So we have CPN in complex situation, and in a real situation, a really interesting case is as follows. Suppose that we have R of some dimension n. So what is CPN? CPN is the space of all one-dimensional complex subspaces of Cn plus 1. Yes, projectivization. But what is interesting in real situation? In real situation, it is interesting to have Grassmannian of two-dimensional subspaces of Rn. So in problem 2c, for RPN it is not interesting. It is interesting for this manifold. For this manifold, it is an interesting problem, and there is an interesting answer. For RPN, the answer is too trivial.
Вот у RPN у него зачислены в гомологии, там есть Z по 2Z.
Да.
А когда мы переходим...
Ну, они все пропадут.
Они пропадут. А что это значит с точки зрения форм?
Ну, нет там формы, все. Все замкнуты.
С помощью форм никак не...
Никак не. В том-то и дело. Кручение мы с помощью форм не видим.
Понятно.
So I suggest you concentrate on these two problems. They are of completely different nature. The second is easier.
Извините, то есть первый это просто надо ручками.
Ну, я говорю, здесь два способа. Можно ручками посчитать, можно понять, почему ответ должен быть таким без всякого счета. То есть она решается без счета. И решается счетом. Ну, как хотите. Можно так, можно так. То есть на самом деле, ну, давайте некоторые подсказки, то, что вы посчитали для φ по c по 1, этого уже достаточно, чтобы дальше сделать без счета. Но в принципе можно сделать со счетом. Ну, как бы. Yes, and the third interesting problem is problem 5 in this list. It is related to these two. Actually, what is this? We at the end of this lecture just at the very end of the last lecture, we see that if we have a compact oriented connected manifold without boundary, and we have a vector space, yes, then we have this Thom isomorphism between, and in particular we have Thom isomorphism between zeroth cohomology here and between if this is of dimension n, then we have here nth cohomology with compact support of E. Yes? What do we see and so here we have 1, and here its image is this thumb class. What do we see in the case of CPN? In the case of CPN, again, it is very useful to understand this case explicitly. In the case of CPN, we have the following nice situation. We have submanifold CPN minus 1 inside CPN. Once we have such submanifold, what do we see? For any submanifold inside a manifold, we have a tubular neighborhood. We have normal bundle, normal vector bundle, whose fibers are okay. At every point of this manifold is CPN minus 1. At every point of it, we have tangent space to CPN minus 1. And we have normal space, which is orthogonal to it. This is Riemannian manifold. We have this Fubini-Study matrix. And this orthogonal manifold can be a nice thing is that the total space of the normal bundle can be embedded as a tubular neighborhood. We'll prove it in details on lecture, but now just let me be not very precise, but we can embed this, we can embed each fiber as small plate orthogonal to submanifold. And together they... Yeah? Tubular neighborhood, да. Это трубчатое окрестность. So this one lives here. The tubular neighborhood lives here. But this tubular neighborhood is actually, this is one-dimensional complex bundle. Yes, this. But I would like to look on this from real point of view. So it is two-dimensional real bundle. Well, this tangent space have real dimension 2n minus 2. In 2n dimensional space, the orthogonal plate is two-dimensional. So what we see? We see, and everything is oriented. Since everything goes from complex numbers, everything is oriented here. All manifolds, all bundles. So what we see? We understand that here we have thumb class, which lives in the second cohomology with compact support. We have this picture with n equal 2. So we have thumb class, which lives in two-dimensional cohomology with compact support of this total space of normal vector bundle, or we can consider this as a tubular neighborhood of CPN minus 1. But now we have this embedding. And in cohomology with compact support, we have push forward, which goes to cohomology with compact support of CPN. But CPN is compact, so we can not consider. I can skip C here. This is just usual de Rham cohomology. So we get into the second cohomology of CPN. And if we solve these two problems, we understand what is the second cohomology of CPN. We now already understand the generator. And a natural question is how this image of thumb class is related with the generator. So we already understand what is the second cohomology, not only on the level that it is isomorphic to R. We understand that it is isomorphic to R, and the generator is that precise formula. So this is R with given generator. And so the question is, where in this picture is this I star of phi? So this is an element of second homology in which we already have generator. So we may ask what is the coefficient. Maybe it is 0, maybe it's not 0. And that is the problem 5 in the list, and actually it can help solve problem 1. But the easiest thing here is problem 2, and actually I would suggest that we start with it. Well?
Ну, просто у нас нужно доказать, что если есть какая-то такая форма, просто в электронном пространстве комплексном, которая вероятно относительно да? Когда если, в общем, если почетно, тогда достаточно задать на таких векторах вида, где вот это нормальный базис, если нечетно, то там, в общем...
А почему только на таких? Если там несколько, почему должно быть именно x обязательно со своим x входить? А если, если я, например, возьму E1, E2, E3, E4, да?
Ну, вот у нас есть мы можем можем высчитать x1 из любого вот из этих с каким-то коэффициентом вещественным. Это не будет менять. Вот. А можем с комплексным, но это уже не обязательно будет 0. Вот мы можем сказать, что, в общем, если мы знаем нашу форму на всех вот таких векторах, то мы можем по индуксу доказать, что мы знаем на всех векторах вида вот здесь сколько-то раз этих ортогональных штук. Ой. А потом что угодно.
Сейчас, вот все-таки давайте конкретно. Вот если я хочу знать, давайте нормированный базис над комплексными E1, EN, да? Вот я хочу знать на E1, 4 формы, на E1, E2, E3, E4. Как, ладно, 2 формы на E1, E2 просто.
Ну, она будет 0.
Почему?
Можем их переставить.
Мы этой самой унитарной матрицей можем... Да, все. Хорошо, да. Так.
По индуксу.
Да, хорошо, значит, достаточно таких, хорошо, достаточно таких и достаточно на одном таком, да?
Ну да.
Поэтому она одна, да?
А если нечетно, то там получится,
пойдем совсем 0.
Что-то ортогональным всем, и можем его заменить на минус его.
Да, и поэтому инвариантов больше нет, и осталось, и в общем осталось показать только что. Ну да, хорошо. Ладно. Вот так. Нет, она была чисто, не было связи с сингулярными гомологией. То есть она была чисто, что у нас есть спаривание между формами, которые не вырождены. Нет, должно следовать один, опять же, с каким-то коэффициентом. Вопрос какой именно? Да, вопрос какой именно. Вам прислали из моей группы Майкопа. Из Сириуса я знаю, что не прислали. Потому что из Сириуса, из Майкопа тоже надо.
Не у Сережи спросить, он просто никак пространно.
Надо. Там это у него подписывать не надо.
А приглашение?
А приглашение надо.
Вы специально писали кому-то, чтобы...
Я писал такому я писал Коле, конечно, а он перенаправил такому Сергею Бутин. Вообще, если написать его, поставить в копию, то будет быстрее. Чем если... Да.
Есть. Ну вот, можно сделать это по индукции, разбив, по клеткам.
Можно, да. Нет, но это как бы план хороший, но только как бы смотрите, если мы уже знаем, что как бы хорошо бы решить эти задачи и не использовать теорему Дирама о том, что дирамовские гомологии изоморфны обычным клеточным. Потому что для клеточных это тривиально, конечно. Если сможете, вот без этого. Но идея хорошая, так тоже решается. Да. Well, of course, it would be nice if you solve problem 2 without using the Ram theorem. The Ram theorem says that the Ram cohomology are isomorphic to usual singular cell or cellular cohomology. We will more or less prove it in maybe next or the lecture after next, but of course it's interesting to understand it just on the level of the Ram homology itself. For cellular cohomology, it is more or less trivial that the cohomology of CPN is only in even dimensions and so on.
So I believe the standard trick here is that use mere Torres sequence that you cover the projective space.
Yeah.
With upper platform.
Yeah, and this is for problem 2. Yes.
Yes.
Yeah, but not for problem 1.
Well, I'm stuck.
Yeah. Yeah.
For problem 4, this is just homotopy to S1. So
Well, not compactly supported cohomology are not homotopy invariant, so that doesn't work.
okay.
Кстати, нам достаточно доказать того, что там только нули, в нечетных размерностях.
Еще вопрос, почему в счетах только по R? И нет
да.
еще чего-то, да?
Моя редактория можно сказать?
Можно. Мы же его доказали, а почему теперь?
Кстати, вот в этом самом разделении, которое типа как клеточное приклеивание, можно просто найти CP3, например, и там оно же разбивается как просто потому, что оно приклеивается. Это и есть то же самое, что в клеточной гомологии.
По сути, да.
И можно по моей редактории.
Так тоже можно сделать, да. Угу. Да?
Почему экспонент интересен, а просто РК не интересен?
Ответ для РПН тривиален.
Вот.
Ничего нету почти. А в Гроссманиане всегда интересно то, чего не тривиально. А в Гроссманиане уже не тривиальный ответ. Ага.
У нас есть формула, называем фи.
Ага. Да. Угу. Та, которая на единице
Да,
интегрируется.
это была мнимая часть там.
Угу.
Да, это было эрмитово-скалярное произведение. У нас очень будет метрика G, которая есть соответственно, которая будет вещественная часть.
Угу.
Вот. И интеграл. Он будет, если сюда n факториал равен интегралу. Это вот так.
Это более-менее, ну, надо разобраться с нормировкой, то есть это, да, если мнимая часть, то так, а если мы на 2π поделили, то чуть-чуть не, ну, там тоже это вылезет, вот, но как бы проблема в том, что, ну, может быть, у вас как-то получится, на мой вкус, это самый простой способ вычислять объем ЦПН.
Нет, просто...
Ну, то есть я бы в другую сторону это использовал.
У нас есть... Ну, как мы получили это уже? У нас было в C+1 мы завели инвариантно относительно поворотов метрику. И можно сказать, что она была вообще на S2N+1, метрика инвариантно относительно поворотов. Потом мы
Да, так можно.
окружности. И у нас это расслоение, оно локально тривиально. Ну и по идее у нас вот эти окружности, видимо, можно сказать, что у нас эти окружности на сфере, они как бы, ну это большие окружности, у которых радиус 1, а вот эта метрика, она получается со сферы, и на сфере она симметрична. Это значит, что это просто стандартная метрика на сфере. Причем мы еще знаем, что вот здесь в точке 1, 0, 0, 0 у нас омега была стандартная, которая dx это y это. Ну, значит, g будет тоже dx это y это. Это значит, что мы знаем нормировку. Ну и по идее интеграл по ЦП будет равен интегралу.
Да, хорошо, так делается. Но только вот очень желательно, ну, смотрите, вот мы фи нормировали так, чтобы интеграл по CP1 был единицей. На самом деле очень полезно понять все-таки, какое здесь число. Ну, собрать это все вместе, да, собрать это все вместе и каким-то образом. То есть, на мой взгляд, это очень сложный путь, но так тоже можно сделать.
Вот.
Ну, отсюда уже, конечно, следует, что не 0. Это вот, из того, что вы сказали, это по-любому, да, следует. Но это и проще следует, да. самом деле хорошо бы на этой неделе все-таки закончить с командировкой. Я вам сейчас доедем до Стекловки, пришлю файл, там это все можно в электронном виде заполнять, то, что у вас на столе лежит. Вот. И у меня уже все заполнено, там фамилию и должность поменять, и, ну, и название доклада. В общем, ну, какие-то вещи не забыть, но в принципе там все. Да.
Ну, получается, что полный план звучит так. Ну вот, сначала принципа 2 нету больше, чем R, потому что есть двойственность Панкара.
Да, почему и что?
Ну, так оно там R.
Не, а при чем тут двойственность Панкара?
Ой, я про CP1, извините.
А, для CP1, да, для CP1,
Размер.
да, для CP1, конечно, R просто, да.
Двойственность Панкара. Вот. А потом начинаем действовать по индукции.
Угу.
И тема вот что. Ну вот, рассматриваем, ну, к примеру, там CP3, потом у него есть приклеенная клетка, в ней берем центр, берем маленькую окружность, потом смотрим до нее дополнение. Ну, как это обычно бывает. Вот, у вас получается разбиение на вот эту окружность и все многообразие. Вот. Одно гомотопически эквивалентное, оно просто стягивается, ну, ретрагируется, точнее, на подмногообразие, получается, да. А там мы уже знаем. Вот. Пойди так. Сразу остается.
Ну, да. И так, вторая действительно так делается, да. Хорошо. Да. Ага.
Ну, тут с умножением повезло, что они в соседних размерностях такие, а вот если такого не происходит, то как можно ли как-то с помощью Мария Виториса умножения?
Не, вообще, как сказать, как правило, у непонятно чего мы не вычислим, в общем, Мария Виториса как гомологии.
Ну,
Так что это,
кольцо как бы.
ну, тоже не. Это как бы для каких-то конкретных, в каждом случае это своя задача. Это не то, что это какой-то общий метод, это то, что помогает.
Я еще хотел спрашивать, если вы не против, пробовал задачку. Я этих гем не знаю, поэтому я хотел, собственно, спросить, в чем разобраться. Вот, во-первых, Инвариантная метрика на группе Ли?
Ну, это инвариантная мера, но это надо взять инвариантную метрику,
Так.
то есть Риманову метрику взять, любую, усреднить.
Это как?
Ну, как у вас группа на себе действует,
Так.
ну вот так же усреднить. То есть вы хотите взять произведение двух векторов, да? Сейчас
поделить на двух.
да. Можно я вам напишу где-нибудь?
Да, конечно. Ну, давайте.
Вот я могу на этом листочке написать, если у вас есть какая-то метрика, да, Риманова метрика, ну, то есть скалярное произведение в каждом касательном векторе, да, вот, то вы можете сделать вот что. Нет, я немножко неправильно говорю. Значит, сначала надо... Да, это я, получится, одно через другое определяю, другое через одно. Это отдельное, в общем, это надо утверждение. Все-таки доказать, что существует инвариантное скалярное произведение. Это некоторые не очень тривиальные теоремы, но и несложные.
Инвариантное скалярное произведение.
То есть существует, да, существует в ее касательном пространстве в единице,
в алгебре.
В алгебре Ли, да. Существует такое скалярное произведение, что если вы берете, существует вот эта штука, да, такая, что если вы берете, ну, группа на алгебре Ли действует сопряжениями, да? Если вы берете вот это, да, то это всегда равно ксии. Вот некоторое утверждение существования.
Существует такая...
Да, существует. Это чисто про алгебру Ли. Вот существует алгебра Ли. Вот. А дальше, ну, да, пусть же, это, по-моему, надо что же компактно.
Компактная группа Ли.
Да. Вот, значит, а дальше вы берете такое скалярное произведение, разносите его при помощи G.
Так, умножение.
Неважно левым или правым, потому что сопряжения его не меняют. По всей. Получаете Риманову метрику на G и берете форму объема. Ну вот так, например, да.
Круто, да.
И вот она мера. Но вообще, наверное, удобнее начинать. Есть совсем такая общая наука, что это на любой компактной группе есть мера. То есть мера есть гораздо чаще, чем метрика. Ну, даже если она не группа Ли, а какая-то там мерская группа, там, ну понятно, топологическая, любая компактная там, топологическая группа всегда есть инвариантная мера, так называемая мера Хаара. Вот, то есть это, в общем-то, более общий факт. Вот, но у нас вообще, как сказать, у нас все группы будут, по сути, матричные, ну вот типа ОН, поэтому вот можно считать, что можно не лезть в общую эту самую. Вот для матричных групп Ли это совсем просто.
Да, понятно. И получается...
Для матричных это так называемая форма Киллинга, это можно написать явно, вот это скалярное произведение.
Можно форма Киллинга?
Да. Два L, да. Ну, это фамилия. Не от того, что там чего-то убивают, а просто это фамилия математика.
Хорошо.
Да.
Я использую формулу из интернета. Любимый фильм.
Ну да, ответ правильный. Вот. Другое дело, что это вот это должно было быть так, это по-другому быть не могло. То есть это на самом деле можно без всякого вычисления понять. Но так тоже верно. Сейчас.
Ну, нам понятно просто доказать, что нету нечетномерных форм.
Нет, ну еще что в четно нет чего-то еще.
Ну это я еще не додумал. Идейно там как бы, ну мы берем стабилизатор какой-то, ну вот это.
Ага.
Ну то есть по сути это форма, и у нас как бы, ну мы как бы должны делать так, чтобы у нас матрички были, ну как бы были инвариантны относительно действий на вот этих координат. Ну вот, а когда у нас как бы нечетно, у нас остается там четное количество координат, и идея, что мы можем в этой подгруппе UN подыскать как бы четную перестановку, которая будет знак давать минус.
Да.
Вот. Из-за этого у нас там омега равно минус омега,
Да.
значит омега 0.
Ну, так можно сделать, да.
А вот для четных как-то...
Okay, it's time to finish. I just would like to say that problem 2, there are several possible solutions, but one of them is to use Meyer-Vittorius sequence and to prove it by induction. To prove by induction that we have nothing but these phi's, if we already know that this one is not Degener.
How was the hint to solve first problem?
For hint for first problem, first you can compute an integral. That's one possibility, one solution. Second, you can think this picture and use it. It's also possible, and also there are other. There are many solutions here. Your solution is also so well. Also possible solution is that you can locally understand the coefficient between phi to the power n and the volume form on the CPN. And the volume of CPN can be understood from other things. So there are several approaches, all of them yield the same answer. Okay, let's finish for now.